Hi, my name is Clayton. I'm one of the tutors in the Natural Sciences Tutoring Center here at Scottsdale Community College. This video is going to focus on IR spectroscopy. So if you're using the Wade textbook in Dr. Mao's class, it is going to be chapter 12 is where our focus is here. IR spectroscopy doesn't really give you the entire picture. So if you just had an IR spectrum, you wouldn't be able to draw the entire structure of a compound. But what it does do is gives you the functional groups a lot of times. So what we're going to do in this video is really just focus on identifying those functional groups when we see them. So I'm going to have a bunch of spectra pulled up, and we'll just kind of compare and contrast them. And for any of the signals, any of the peaks, we'll kind of go through what the important ones are for you to know. All right, so let's go ahead and jump right into it here. First, I have three different spectra here, and you can see the compounds right here. Oops, what did I just do? There we go. Right here. So this is just an alcohol. This is a carboxylic acid, and this is an amide. All right, so first things first. We want to talk about the, what's it called? The fingerprint region. That's like right around here. You don't need to know anything on the left or the right side of this, because all that gets real jumbled up. If you're doing this as your profession, if this is your job, later in life, you become a chemist and you're, characterizing compounds, things like that, you're probably going to have to know what that stuff looks like. But for our purposes in this class, you don't need to worry about anything below like 1400, 1500 fingerprint region. Don't worry about it. We're looking at everything to the left of that line. So all this stuff in there we don't care about. The OH is characterized by this guy right here. So if you look in like a textbook at a table, it often says that an alcohol signal or peak or whatever you want to call it is broad and strong. So strong is a reference to how far down it goes. The more polar something is, the stronger the signal will be. So this goes down really far, so we know, OH, okay, that's going to be pretty polar, so we could expect a strong signal. Broad is a reference to kind of how rounded this thing is. See how kind of rounded it is? And let's just compare that with this right here. That is sharp. This right here, that is called sharp, whereas this kind of rounded, that's broad. So if you see around 3300, you see a broad, strong peak, that's most likely an alcohol. So we can identify that right away. Let's talk about these guys right here now. These are going to be CH stretches. So right here where carbon is bonded to a hydrogen, those are going to be in right around 3000. So if it's an sp3 hybridized carbon, so sp3ch, or otherwise known as like an alkane, it's going to be less than 3000. So, and you can see here, this is just to the right side, just underneath 3000. So that is indicating that they're alkane. CH bonds. I don't think I have any alkene bonds on this one. We'll compare those later. We'll look at that a little bit later. All right, so that's everything we can do for this one right here. We have our alcohol, we have sp3ch. And again, can I tell the entire structure from this? Absolutely not. All I know is it has an alcohol and it has an alkane, at least some alkane portion to it. Let's look at the next one here. So here we can see, this technically it has an alcohol group on it. Now it's a carboxylic acid, but there is an OH group. But it doesn't look the same, right? So here that is a carbonyl. So that's your C double bonded to an O. That shows up right around between like 1700. And then our OH here is actually muddled a little bit because of that. And so if you see this kind of merging into the 3000s here, where we have our sp3ch bonds, we know that that's like a distorted alcohol, and if we see it in conjunction with that, oh my goodness, okay, there is a carboxylic acid. So this plus this tells us carboxylic acid. Once again, right here, these little peaks in here, those are sp3ch bonds. Let's look at our last one here. This is an amide, so a carbonyl bonded to an amine, basically. Or you could think of that as a carboxylic acid, where you replace the OH with an amine. This is a primary amine, which means it has 2 H bonds. That shows up here. We have 2 peaks. So similar to where an OH shows up, the NH shows up in the same general region. And I'll put a chart up, a table up to show kind of where all these bonds show up in that table. The tables that I'm going to put are from the Wade Organic Chemistry book, and I use the 6th edition, so they're pulled right out of that book. For me, they're on page 531. Anyway, so the OH and the NH are going to show up in the same region, but you can see how different they are. NH, they're sharp, whereas OH is broad. And so here, if I see this, I know that that is an N bonded to 2 H's because I have 2 distinct signals. But if I instead see this, I know that's an N bonded to 1 H, and then it must have, you know, two other R groups bonded to it, right? And so this would be let me use a different color. This is a primary amine. You can see those 2 peaks right there. And this would be a secondary amine with just the 1 peak because there's only 1 bond to an H. From here, we could predict that a tertiary amine would not show any bonds in this region because there are no NH bonds. That is the NH bonding region. If it's a tertiary amine, there's no bond to an H. So we can, that's how we can differentiate between the 3 amines there. All right, let me erase something real quick. Let me get rid of that. All right, so that is our amine. And then once again here we can see our CH, and those are alkane bonds, CH bonds. And then here, because it's an amide, once again, I would expect a carbonyl. This is a strong, sharp peak for your carbonyl bond right here, okay? So because it's an amide, I would expect that as well, just like we saw in the carboxylic acid. All right, so that is how we can kind of differentiate between those 3. Let's move on to the next group that I have prepared. Okay, so our next group of compounds, really all I wanted to do was differentiate between these carbonyls right here. And we see that we have a benzene ring, and here is just a regular cyclohexane. So the carbonyl, right around 1700. Again, we don't need to know anything on this side. So this C double bonded to O shows up in the same place in both of these roughly, right? 1700, strong, sharp peak. That carbonyl, that needs to scream at you, okay? Just like the alcohol should really stand out. A carbonyl should really stand out. Now let's differentiate these portions here. So first of all, if we look at this region here, it's like super flat. Here, I kind of call that just like garbage. There's a little bit of garbage in this IR spectrum. And so whenever I see this it's like kind of rising up a little bit over here, Whenever I see that, now I've been doing this for a while, but whenever I see that, I think, okay, there's possibly an aromatic involved. If we don't recognize that, that's totally fine. That's kind of a minor detail. More importantly, if we look right here at these peaks, these are on the right side of that 3000 mark. And so I know these are sp3 CH bonds, or alkane bonds, just like we saw on the last one. Here, there's the 3000 right there. Once again, we also have those. So we have sp3CH, sp3CH, or alkane bonds. They're going to be just short of the 3000 mark. But on the one with the aromatic here, I know that there's an H. Here, let's just draw this out. I'm going to have an H on all of these. Well, these are sp2CH bonds. sp2CH is going to show up just on the other side of the 3000 mark. Okay, so these right here are sp2CH. Interestingly here, these sp2CH bonds are a little bit muted, and that's kind of an effect that this aromatic has as well. We might normally expect them to show up down here more, but this aromatic kind of, again, it muddles them a little bit. I call that garbage, you know, and that's just my own made up thing, you know, but that's kind of the impact that this aromatic ring has on it. So here, anyway, we can see there are sp2CH and sp3CH bonds, whereas this one, we would only expect sp3CH, and sure enough, that's all we can see. And then both of them, of course, have the ketone, your carbonyl group, around 1700. All right, let's move on to the next one. Okay, so for our last group here, what I wanted to highlight was this right here. We have a triple bond, carbon-carbon triple bond, and a carbon-nitrogen triple bond. So this we know is a nitrile. This is an alkyne. So I'll just write that down, nitrile. And this is an alkyne, Y-N-E. And this bond right here, that would be an sp-CH bond. This carbon is sp hybridized. Which of course we know sp3 shows up in a certain area, sp2CH shows up in a slightly different area, and sp-CH will show up in another different area. So we'll highlight that as well. All right, so the triple bonding region, and again I'll put that graph up or that chart up real quick, the table that shows kind of where the bonding regions are. The triple bonding region is going to be like 2300-ish. So that peak right there and that peak right there, that's the triple bonding region. And what I really wanted to highlight, see how low this one comes down and see how low this one comes down? Our nitrile is substantially stronger than our alkyne. And so that is a reflection of the difference in the polarity of those bonds. Again, a more polar bond will show a stronger peak than a less polar bond over here for our alkyne. And so that's just something to keep in the back of your mind, right? If you see a triple bond in this region, we should be thinking, okay, what could it be bonded to? If it's this strong, it's likely not going to be a carbon-carbon bond, because we already know that's going to be less polar. All right, so that is kind of the difference between the nitrile and the alkyne. Now let's focus on the rest of it. All of these hydrogens are sp3CH. So sure enough, right here, there's our line. And look, it's not exact. Looks like that's maybe just on the other side of 3000. Right. I mean, again, this isn't all perfect every time, right? Every compound is different, and every compound is going to show a different fingerprint or thumbprint or whatever on this spectrum here. And so what you need to have in mind is, okay, sp3CH, that is going to be less than 3000. generally speaking, none of these are perfect, right? And so these are generally less than 3,000 sp3ch. Here, once again, generally less than 3,000. So I have some sp3ch. Where are those located? Those are right here. This one, though, that is right here. That's my sp-CH bond, my alkyne bond to a hydrogen. So that shows up right around the 3,300 range. All right, so I think that will do it for this video. The next video will be talking about, I think, mass spectrums briefly, and then we'll go to HNMR. All right, thanks. See you.